This is units 1.9 and 1.10. This will be trophic levels along with thermodynamics and energy flow. Section 1.9 is about trophic levels, so we're briefly going to revisit the food chain here, right, where the sun is the source of ultimate source of energy, which producers use to make food. Primary consumers eat the producers, and secondary consumers eat the primary consumers. Tertiary consumers eat the secondary consumers. And each of these roles, producer, primary consumer, and so on, are considered trophic levels. So in this food chain, there are 4 trophic levels. It's a little tricky to remember because the producer is the first level and the primary consumer is the second level. But usually you don't have to remember that so much. Just have to know that there are different trophic levels. The other thing to remember is that the arrows follow the flow of energy because the sun is the primary source of energy that goes to producers, and so energy always goes upward in the food chain. So the lowest trophic levels are, the producers, and then energy flows upward. And we're going to connect this to thermodynamics, which is the next part of our screencast 1.10. So animals and plants need energy because they need to do work or transfer heat. In the case of animals, which are generally heterotrophs, they need kinetic energy to move around to find more food because the food is not always near them. Potential energy is stored energy. So plants will make their own food, but then they will also store it because they have to survive at night, when the sun is not shining. So we'll look at these 2 types of energy generally: kinetic energy to move around, potential energy that is stored. The first law of thermodynamics, of course, is that energy cannot be created or destroyed. It can only change form. So we're looking at chemical energy that can be changed to kinetic energy, right? That's what animals do. Plants change light energy into chemical energy. So the animals are able to get the chemical energy from the plants by eating them. That's one way it changes form. Second law of thermodynamics is considered the increase of entropy. And so that as energy changes forms, the quality of that energy always decreases, that it becomes less efficient as you go higher up in energy transfers. So energy efficiency is how much useful work is accomplished before the energy changes to its next form. If you look at a ranking of sources of energy and their relative energy quality, you can see at the top, high amount of energy quality is electricity, very high temperature heat that's greater than 2,500 degrees Celsius, nuclear fusion, nuclear fission, concentrated sunlight, or high velocity wind. These are all high quality sources of energy. We can use that for things like industrial processes and producing electricity or running electrical devices. Slightly below that are things like fossil fuels, which we can use to move vehicles. Below that is sort of like normal sunlight, water flow, geothermal energy is of moderate energy quality. We can use that for sort of like home applications. And then the lowest energy quality is like low temperature heat below 100 degrees Celsius or dispersed geothermal energy. And all that's really good for is space heating. So how do we fit into this whole issue of energy quality? So our enjoyment of life, we want to reduce local entropy, right? We want to keep our temperatures cool. We want to construct houses so that we have shelter. But this is at the expense of polluting the environment because of byproducts of producing energy. Another important law that is going to relate to all this is the law of conservation of mass. So for any closed system, the mass must remain constant over time. And it's also true that mass is not really created or destroyed either. So really what's happening when we make products, when we burn fuels, we don't really consume resources, but we're really just transforming them into a different form and that results in a loss of useful energy because of the law of thermodynamics. Because the law of conservation of mass, the mass is still there, but we've changed its form and probably made it less useful in the process. And so this is relevant to environmental science because of pollution, right? If the mass is still there, but we've changed its form, then it may not be useful anymore and we have to dispose of it somehow. And too often it's disposed of by just throwing it in the water, throwing it in some hole in the ground, and that becomes a problem for pollution. Same for burning fuels. Really burning anything produces some kind of air pollution that we need to deal with because it's really just going up into the air. Consider this relative comparison of resources. A person could survive on 300 trout for a year, I guess, if you had, it's got to be a pretty big trout. But the trout have to consume 90,000 frogs, and those 90,000 frogs consume 27 million grasshoppers. Those grasshoppers live off of 1,000 tons of grass. So you can see how much grass needs to be grown in order to make those 300 trout. When we get to agriculture, you'll see the numbers for things like chicken and beef are much, much higher. So ecological pyramids are one way that we organize this information. And energy pyramids are sometimes also called trophic pyramids. And so this is kind of our connection between trophic levels and the laws of thermodynamics. We're also going to see biomass pyramids, and just for comparison purposes, we'll see a pyramid of numbers. But these ecological pyramids are going to be ways that we analyze number of individuals in different populations and how they relate to each other in a food chain. We could consider these graphical models, right? That's why they are pyramids, because they're not just a chart of numbers. So usually pyramids become narrower to the top. That's why we're going to call them ecological pyramids, but we're going to find in some cases there are inverted pyramids, and we're going to have to understand why that's happening. All right, so pyramids of energy. So consider this pyramid. It doesn't look like too much like a pyramid because things get pretty narrow pretty fast. But consider in this example, you have 807 producers that support 37 herbivores, and then 11 carnivores are supported off eating those herbivores. And then the top carnivore, there's just 1.5 of them for all those 807 producers. And so what we're seeing here is what we're calling the 10% rule, where only 10% of the energy flows from trophic level to trophic level. At each transfer point, from the producers to the herbivores, 90% of the energy is lost. From the herbivores to the carnivores, another 90%. And so you can see now why there's so few carnivores, and especially so few top carnivores for the amount of producers that are there, because every time you're losing 90% of the energy. By the time you get up to the carnivores, you've only got really like 1/1000th of the energy that was present at the beginning, at the bottom of the food pyramid, or energy pyramid, excuse me. And so we could calculate a conversion efficiency, but generally it's going to be around 10%. So where is this 90% of energy going, right? Because we said energy can't be created or destroyed, it only changes form. So some of the energy is lost in feces and urine, and some of it is used in respiration, right? And then lost as heat. For example, humans, right? We respirate to stay alive. We need to keep our bodies at a certain temperature. And so some of that energy is just lost as heat to keep our bodies at the temperature they need to be. And then other, energy is lost through excrement. There are also pyramids of biomass, right? So biomass is the total mass of organisms. Like if you took 800 plants and you massed all those plants, like that would be their biomass. And of course, we're going to measure that in grams or kilograms. If there's mass that is missing, right, if you make a pyramid of biomass, and of course the mass gets smaller as you get to the top, the issue is that there's mass that is detritus and then becomes decomposed. So consider this biomass pyramid where you can see at the bottom you have 2.0925 times 10 to the 7th kilograms per kilometer squared of grass, but then less of the snowshoe hare and less of the red fox and even less of the wolf. So there's a lot of biomass of grass required in order to support that biomass of wolf. We're always going to measure biomass in what says weight per unit area, but it really should be grams per square meter. That's what we're looking for. The final pyramid we can look at is just straight numbers, right? So how many producers, how many consumers, how many secondary consumers, how many tertiary consumers. And this is a little bit easier because you can just count the numbers as opposed to having to mass them. A lot of wild animals can't be massed. So sometimes it's easier to just count them. Now, one issue you will see is that pyramids of numbers vary depending on ecosystems. So on the A pyramid, we have a typical pyramid that shows, large number of producers, which produce a smaller number of snails, smaller number of mice, and an even smaller number of owls. But compared to B, you have one large producer. You can have lots of caterpillars living on that producer. So you can have one tree that supports a lot of caterpillars, and then a smaller number of bluebirds eat those caterpillars. And then finally, C, you have an inverted pyramid where you have one rose bush that is a source of food for aphids, and then parasites eat those aphids. But a lot of parasites can live off of small number of aphids, which obviously live off a small rose bush. So sometimes inverted pyramids of numbers can be inverted based on what type of ecosystem you're looking at. So again, some more examples of inverted pyramids. It's possible to see these not only in pyramids of numbers, but also in pyramids of biomass, depending on what kind of organisms we're looking at. And part of the reason for this is because sometimes the producers will grow faster than the consumers. And so the consumers, there's seemingly an equal amount of biomass, but it's because they're consuming all the producer biomass. We will be doing a lab with this, but it does happen more often with number pyramids. Inverted pyramids can happen sometimes based on seasonal fluctuations, weather, or natural disasters. Here's a good question to think about. Can an energy pyramid ever be inverted? Consider the possibilities. What do you think? And how are the laws of thermodynamics relevant to that? Right? How is energy different than numbers and different than mass? That's it for units 1.9 and 1.10. Let me know if you have any questions.